Hello everyone. In this playlist, we're going to be exploring chapter 6 in the main text. We're going to be learning about a few additional issues that crop up when we run linear regressions. This video in particular will go over the topic of data scaling and what it means for statistical inference. And we'll also be looking at a particular type of regression where every single variable has now been standardized. So let's get into the first one, which is data scaling in inference. What is data scaling? Now, if you take any one or more variables in your data set, and if you rescale that variable by a factor, meaning if you multiply or divide it by some constant, then you've effectively rescaled the variable, and this process is called data scaling. For example, if you have a data set where one of the variables is income, and suppose income is measured in millions of dollars, but you want to have income measured in billions of dollars because it just cosmetically looks better with fewer digits, then you take every single observation that is in millions, divide it by 1,000, and the result that you get is going to be income in billions of dollars. So this process is just called data scaling. Now, in the context of regression, one could think of rescaling the dependent and or the independent variables. So when that happens, what does it do to the coefficients of the regression analysis? What does it do to the beta hats? What does it do to the standard errors? And how does this process change the way in which we do statistical inference? So that's going to be the subject of the next few slides. So let's see how that pans out. So in this particular slide, I'm primarily referring to just a simple linear regression model. So imagine a single dependent variable y and a single regressor called x1. Now let's look at each case one by one. So suppose we take the dependent variable y and we're scaling it by a factor of c. Meaning, I take every single observation in the column y and multiply every observation by the number c. Now, what happens when I run a regression of this rescaled y on my regressor x1? Turns out, the coefficients that you get from the regression, beta naught hat and beta 1 hat, the intercept and the slope coefficients, are both going to be scaled by the same factor c. So this is fairly easy to remember. When you rescale y by c, all your coefficients are going to scale by the same constant c. Now, what happens when you rescale a regressor x1 by c? So when you change a regressor, when you rescale a regressor, turns out nothing happens to your intercept. Beta naught hat doesn't change, but the coefficient, the slope coefficient associated with that regressor, which is beta 1 hat in this case, is going to be rescaled by the reciprocal of the constant, meaning beta 1 hat is now going to be multiplied by 1 over c. This is the change that you'll see in the regression table. So the table now summarizes how the coefficients change. What about the rest of the things that we care about? Standard errors, t-stats, and x-stats. Turns out, the standard errors change in exactly the same way as the beta naught hats. So if the beta hats are scaled by c, standard errors are scaled by c. If beta naught hat doesn't scale up, doesn't change, standard error doesn't change. Beta 1 changes by 1 over c, standard error changes by 1 over c. So it exactly mirrors the change in the beta hats. So, okay, coefficients down, standard errors down. What about t-statistics? Well, if you remember, t-stat is defined as the beta hat minus the hypothesized value by standard error of beta hat. Now, if I assume that the hypothesized value is just 0, the t-stat simply collapses to a ratio of the coefficient to its standard error, of beta hat to its standard error. So generally, when we refer to t-stat, that's what we're talking about. There's an implicit assumption that the hypothesized value is 0. So look at the t-stat on the slide. If beta hat and standard error are changing by the same factor, then t-stat is not going to change. So the t-stat remains the same, and therefore our hypothesis testing process doesn't change. our statistical inference also remains what it was before the rescaling happened. A similar conclusion applies to F statistics as well. Based on some more material that we'll learn as we go through the slides, we'll be able to figure out how and why the F stats don't change. But that's an exercise for you. So the bottom line is hypothesis testing is invariant to how we scale the model variables. So let's look at an example to understand how this works. So here is a regression where the dependent variable is the birth rate of children, and that is being regressed on the mother's smoking behavior. So the number of cigarettes smoked by the mother, smoked per day by the mother when she's pregnant, and the income of the family in thousands of dollars. And the regression table on the slide gives you the results of this regression. Now, if you look at the table, we can gather the impact of cigarettes on the dependent variable. So the coefficient here is minus 0.4634, which says that for one more cigarette smoked per day, the child's birth weight in ounces goes down by 0.46 units. So to make it a little bit more interesting, if the mother smokes 5 more cigarettes in a day, then the birth weight goes down by 0.46 times 5, roughly about 2.3 ounces. So we interpret the coefficient now. And if we want to understand its statistical significance, then we need to compute the t-stat. Now, in this particular regression table, the standard errors are given in parentheses. So below every coefficient, the number within the brackets is the standard error associated with that beta hat. So given the coefficient and the standard error, we can now go ahead and compute the t-stats. And if the t-stat is sufficiently large in magnitude, then we know that that variable is statistically significant. So let's go ahead and find that. T-stat is now minus 0.463 divided by 0.092. Turns out it is minus 5.06, which is it's a t-stat in the extremes of the t-distribution. So telling us that this variable is indeed significant. So that's the story with the original model. Now let's go ahead and rescale the dependent variable. Suppose we want to measure the weight in pounds. So initially it is in ounces. Now we want to measure it in pounds. And 1 pound is actually equal to 16 ounces. So to go from ounces to pounds, all we have to do is divide every observation by 16. So we thus generate a new dependent variable, birth weight in pounds, given by the original variable divided by 16. Now, when your y variable changes and you estimate the regression, remember every single coefficient in the regression is going to change in the same way as the y variable. So effectively, the estimated equation after rescaling becomes this. Birth weight in pounds is just birth weight in ounces divided by 16. And you notice that beta 1 hat, and beta 2 hat are all being rescaled, and they're all being multiplied by 1 over 16. And let's see how that looks like in the results. So in the table here, the second column shows us the results for this rescaled regression. Now the coefficient here on cigarettes is minus 0.0289, which means for 1 more cigarette smoked per day, the birth weight of the child in pounds goes down by 0.03. For 5 more cigarettes, it would mean about you just take the coefficient multiplied by 5. The answer that you get is 0.1445 pounds drop in the birth weight. Now, we can very fluidly move from pounds to ounces and back. 0.1445 pounds is just, if you multiply it by 16, you get the answer 2.321 ounces, which is similar to the result we saw earlier. So the story matches up. So even if your beta hats are in a different, are now rescaled, the underlying intuition or interpretation stays the same. Let's see what's happening to the standard errors. And maybe this is something that you can check out. Turns out 0.0916, which is the standard error in the first case, divided by 16 should give you 0.0057, which is the standard error in the rescaled case. Beta hats and standard errors will change in the same manner, will scale in the same manner. And therefore, our t statistics does not change. It's the same as before. So our inference remains as it was earlier. Now, what happens to the confidence intervals? Well, the confidence intervals are just a margin of error that we draw around the beta hat coefficients. And this margin is just the t critical value multiplied by the standard error. If beta hats and the standard errors are both changing by some factor, the confidence interval, which is just a linear combination of these two terms, is also going to be scaling down is going to be scaling by the same factor. And therefore, in this case, if beta hats and standard errors are scaling down by 16, a factor of 16, confidence intervals will also scale down by the same factor of 16. Think about it in another way, it will make sense. Notice the coefficients on cigarettes in the first two models. The number in the second case is a lot smaller because you're now measuring birth weight in pounds. So if my beta hat coefficients and the standard errors are smaller, the confidence interval is going to be just centered around those smaller numbers. And it's going to be tighter around just those numbers. And that's why we say that, and that's because confidence intervals are scaling down by the same factor. What happens to R squared in the regression? R squared doesn't change. And why is that so? R squared is just 1 minus SSR by, sorry, this should be SST. So the residual sum of squares, SSR, that is just going to be your sigma ui hat square, right? Well, if everything in my regression is scaling down by a factor of 16, the residual is also going to be ui hat by 16. And therefore, the residual squared is going to be ui hat by 16 the whole square. So the residual is SSR is going to scale down by a factor of 16 square. The same thing happens to SST as well. That will also scale down by a factor of 16 square. And these two will cancel out each other, and therefore your R square remains unchanged. R square is your coefficient of determination. That doesn't change. R square is also a measure of how good of a fit your regression model is, and it measures how good of a linear fit your model is. Rescaling doesn't change anything in that context, and therefore R square stays the same. And you can numerically check the SSR values in the two columns to see how this scaling process is happening. All right. So now we've seen how rescaling happens with the y variable. Let's see how rescaling plays out when we rescale one of the covariates, the x variable. So let us now define cigarette consumption in packs of cigarettes, which is a fairly realistic thing to do, right? Generally smokers will consume cigarettes in packs. So if we were to rescale that variable, a pack of cigarettes has 20 cigarettes. So if we were to go from measuring cigarettes in terms of individual units to cigarettes in terms of packs, we have to just divide that regressor by 20. So my x variable is now going to be scaled down by a factor of 20. I'm going to multiply every x by 1 over 20. So when that happens, remember, the beta hat and the other slope coefficients won't change, but just the beta that is associated with the changed rescaled regressor will now get scaled by the reciprocal. So let's see what's happening here. So to go from number of cigarettes to packs of cigarettes, the x variable now becomes cigarettes over 20. And therefore, just the coefficient associated with that rescale variable will be 20 times the original beta 1 hat. And when you run the regression, you will see that the coefficients reflect exactly this pattern. So initially, when we ran cigarettes in just units, our coefficient was minus 0.4634. When we run cigarettes in terms of packs, the coefficient is minus 9.268. And this number is nothing but minus 0.4634 times 20. And you're welcome to check if that holds true. The standard errors also follow the same path, and therefore the t statistics don't change. R squares also don't change. And so our statistical inference continues to be the same. So this summarizes how rescaling works in the context of our linear regression models. And I realize I'm out of time to do standardization, so I will do that in the following video. I will see you there.